Let me just start by introducing the team. So in the middle, we have Meixi. So Meixi is like a 1 in 8, 9-year PhD student. Not only is she absolutely brilliant, but she can just follow things through from start to finish and just get it done when you really need to. Reza is an applied statistician, always making sure that we have the long-term goal in sight and making sure that our efforts are concentrated and moving in the right direction. And there's me, and I'm sort of the know the software and also like the details guy. I'm the one going through like the LaTeX bib, making sure everything is sentence case and so on and so forth. So extreme value modeling, I take it that the two other talks today have already, in this room, have been on this topic, so maybe I won't spend too much time on background. But this is particularly important now in all sorts of fields: climate, traffic, hydrology, meteorology, and so on. So a little bit of theory first. So this is really not my strong suit, so I'll just go very high level over this. But it seems that if you take IID observations from any old distribution, epsilon, like plus or minus a bit of math here, but it turns out that if you take this type of limit, you take their maxima, and then you have like some sequence of, let's call it location and a scale sequence, they're going to converge to some distribution which has got to look like this. So either it's going to be that form above, or it's going to be the form below. I remember the name of that one. That's the Gumbel. And then over there on the right-hand side, you see there's this kind of restriction. So that's a support restriction, which I'll get into in a second. So what I'll refer to as the generalized extreme value distribution is the location scale version of that. So just take that kernel, and then you can move it around and scale it a little bit as well. That's the form that we're going to use for modeling. Let me show you a couple of them here. So I let that shape parameter, that's really the interesting one in terms of what this thing looks like, and I let it go a little bit between negative and positive values. The main thing I want you to see from here is just the flexibility in terms of left tail, right tail, but also very annoying for us on the modeling side is the support. So the support is not, it's not the whole range, and in fact sometimes there's a positive upper limit, sometimes there's a lower limit, and sometimes it's the whole thing. So it's a little bit difficult to work with on the computational side. OK, so what kind of data do we have here? So we had some extreme value measurements. So let's say we had different locations. And I will present the application that we looked at here. But you imagine you have spatial locations. And at each one of them, we have these extreme value measurements. Let's say they're IID. We have the location of each of the stations, so the coordinates. Oops. And then just for simplicity, I'm going to say there's no other covariates here. So whatever I'm going to show you, it's not going to be hard to stick them in, but just to keep it like, in terms of what's high level and how the pieces work, I think this is good enough. So here's the first level of our model here. It's just pretty straightforward. You just say to yourselves, well, the parameters of the GEV are simply going to be location dependent. That's it. Just a nice simple model. The next sentence, this is the first typo found in the slides. This next sentence is not right. This is our modeling decision. We decided to constrain the shape parameter in such a way that we're only going to get, we're not going to have an upper bounded distribution. We're going to have a lower bounded distribution from the negative side. And this was sort of, it's not written properly here, but this was just a modeling thing. We were thinking to ourselves, look, we're going to be, the theory is one thing, but on the applied thing, we're looking at, in our case, we were looking at snowfall. It's positive valued. I feel uncomfortable having a distribution modeling that has an upper bound and no lower bound, like it can be down to negative infinity. It just seems weird. So we just constrain the shape. We got into an argument with the referee about how to do this. There are other ways. If anyone has a better way of doing this, I would love to discuss it. But this is the best that we came up with for this paper. So this is the model we use, but it's not the only one. You don't have to do this. And in fact, a lot of the pushback on this is that conditional independence. Does it really make sense? You have these independent, at each location, the GEV parameters are conditionally, well, the data are conditionally independent given the parameters. So just a couple of alternatives people have looked at. They looked at sort of this big copula model on all the data. So that allows you to have dependence between locations. Another one was like, I think this is really cool, but it allows you to have marginally GeV at each location, but it's like some spatial process that you can have GeVs everywhere in a very smooth way. This was all reviewed in a paper in 2012, where it was found that, look, if what you're after is the codependence, then it's better to model these things as the conditional dependence is too much. But if what you're after is location-specific things, then it turns out that this sort of conditional independence is giving you something a little bit better. So it's like, depending what your downstream analysis is, one may be more or less useful. So in our case, really, we were trying to give location-wise information, location-wise assessment, so it made more sense for us to use this form. All right, so how are we going to do the spatial modeling? Well, you could do it using basis functions. That's great. We decided to do it using Gaussian processes. So sort of to me, a pretty natural way of doing this. So just a very brief primer on Gaussian processes. If I can just say it, a Gaussian process is some process indexed by whatever. You take any finite index sets. In this case, it's just locations. So take any finite set of locations, and the distribution on those at those locations is multivariate normal. So it's just like whatever your multivariate, it's just the extension of multivariate normal to arbitrary sets. So there's a mean function we have to define, and there's a covariance function as well. So in our case, the mean specification, we just did regression. This is the most straightforward one in our minds. So we reduce everything to this, like just the linear coefficients. On the covariance scale, the one we picked was Matern. I want you to just, I figured, look, it's not going to do much if I write down what that kernel is, that k of nu. So instead, it's just, let's focus on the bigger stuff that's going on here. The first one is there's a magnitude parameter, so it's just the amount of variation. The other one is the range parameter, so it's just the correlation, the spatial correlation. That's another modeling parameter, how much information you want to borrow or how far you're willing to borrow information in each location. And the final one is the one that we won't get into too much here, and I'll tell you why in a bit. But this is the smoothness parameter of whatever this process is. So it turns out that nu, it's like it has something to do with differentiability, but we're just going to say let nu be equal to 1. And I'll mention a little bit more why that is. So at least the other two parameters, those are sort of more. I have a better sense of those, in terms of what they would change than maybe the last one. All right, so here's what the whole model looks like. It's your good old hierarchical model for. So we got the data level on top, where those are the data that are conditionally independent given the parameters, and then each of the parameters has its own Gaussian process model. We've got just a bit of notation. Here are the observations. Those are the y's. The random effects, as I'll loosely call them, that's just the GeV parameters. But just again, relating back to the hierarchical modeling, random effects was a nice word to use. We have at each location and also each of the three different parameters. And finally, we'll just say hyperparameters. So that's all the rest of the stuff here. So this would be the regression coefficients, and then the location. And then the scale and correlate and spatial correlation parameters for each one of the GeV parameters. So this is our model. Just pausing a little bit to absorb this. This is kind of like key point number one. This is the model that we want to work with. All right, a couple of challenges. So here were the two main challenges that we encountered. There's the model up there. So number one is, well, the random effects are difficult to integrate out. There's no closed form for this. You can certainly write down the complete likelihood of both the observations and the random effects, but it's difficult to integrate the random effects out. And then number two, so this is a problem that plagues a lot of spatial analyses with Gaussian processes, at least, is that the computations scale very poorly. If you have this, so we're looking, let's say, at finite, we have n locations. Well, every time I want to write down the multivariate normal on those n locations, there's an n by n covariance matrix lurking in there. You want to get your multivariate normal PDF or sampling or whatever it is, that involves, that scales cubically in the number of locations. This is very bad. You want to do like a big spatial analysis on several thousand locations, that's starting to waste a lot of computational resources to do that. All right, so let me go through the approach that we used on each of these issues. So the first one has to do with the marginal likelihood. So here's what we did. This is, the Laplace approximation. I love the Laplace approximation. I'll tell you a little bit about why when we get there. But for now, I'm going to flatter myself in saying that I can explain this to you in 2 points. Okay, what's the Laplace approximation? The goal is I want to integrate out those random effects. I can write down the integrand I can write down in closed form, that's fine. The integral, though, I can't compute. What am I going to do? So step one, I'm going to say the thing I want to compute is actually a ratio of two things. All I've done there, if you look at this, you stare at it for a little bit, you'll realize that's just the definition of conditional distribution, but I've flipped things around a little bit. So normally the conditional appears on the left, and the marginal is in the denominator, and I just switch those. And what's interesting here is that this works for any value of u that you want to plug in. We'll just call it u hat now. So what's left? If I have this, so what the spirit of Laplace is, look, you know the numerator, that's easy. Try to plug in an approximation for the denominator. So what's the natural one? The natural thing there is, of course, is going to be some sort of normal Taylor expansion, however you want to say it, but that's what's going on. So you say that denominator there, it's a normal. The mean and variance are going to be done via mode and quadrature, so whatever is the mode of the actual conditional and then just the quadrature there. And then the value at which we're evaluating it is also the mode. So the mode gets used for two things. It's the mean, it's the u hat at which you're evaluating, and then we have our usual Hessian matrix, which we invert to get the variance. So that's it. That's what Laplace approximation is. To me, it's beautiful, it's simple, and in many cases, it can be very effective and very fast, of course, compared to the full integration. Once you do the math of all this, it turns out that this just reduces to a very simple form. So you've got the mode sitting over there, you plug that into your joint distribution, and then you have you got to take the log determinant of your Hessian. All right, so this is great. I'm just going to place these all up here. I don't want to spend too much time on this. Again, what I had in mind when I made this slide was like, let's go through all the inference we can think about. It's not like, there's nothing specialized about this. These are all very general things. I'm just saying you could do an MLE. You could just, do good old MLE Fisher information, but using the Laplace approximation instead. You could do what we colloquially call a Bayesian normal approximation, which is where you get the mode and the quadrature not of the likelihood function, or the log likelihood, but rather of the log posterior. And then just pretend that it's a that your posterior is normal with that mean and variance. So computationally, this is like the computational analog between what we would do for MLE Fisher in the Bayesian case. And if you want to do full, proper Bayesian inference, you can just do whatever it is you would do on the Laplace posterior instead. But the key point here is what I was thinking in my mind was, they'll think about the computational methods that will be required here. What would I need to do? Okay, so that was what this was supposed to be. So it's evaluating and also gradients of whatever that top thing is. So gradients with respect to theta. Now in terms of the random effects, it's so here we decided to do it in a Bayesian way. Really, it's just like, this is my personal opinion, but I find that treatment of hierarchical models, random effects, it's conceptually it's very easy from a Bayesian standpoint. So we just kind of followed that thread. But in this case, you start off working on your marginal. You do whatever inference you want for that. And then the other step, you just do using your Laplace approximation. So that second line there, that's just the normal approximation we use for the conditional in the original version of Laplace. It's whatever we used as the approximation of the denominator. So that's great. You can think of this as a two-step sampler, sample from the marginal, and then combine each marginal hyperparameter sample with a draw from the random effects. But it's quite expensive. Every time you need to do a mode quadrature, this is starting to take time. I'll show you some timings later, but this really destroys a lot of the speed. Something a lot faster is we look at this way. We say, okay, again, keep the first part. Now let's just do Bayesian normal approximation. In other words, mode quadrature on the log posterior. Very, very fast. How do you do the random effects? Well, instead what we do is we say, take that second line on top, linearize it in the mean, and just keep the variance constant, and now I get to have something jointly normal. So now all of a sudden, everything is just going to go much faster. I can do like a one-time calculation of all this, and now I can just sample from this. It's now normal in the hyperparameters, and then conditionally normal in the random effects, and now it's very, very fast. Okay, so this is also cheap to draw from. Return level. So this was actually our main quantity of interest. So the idea here is we're interested in the upper quantiles of the underlying GVV distribution at every location. So the way to think about this is the 10% return level, roughly translated, that's like the value that you would expect to get once every 10 years on expectation. That's how long it takes to get that. So this was so this is something that's used very often in many in climate extreme value settings. Turns out in this case, this is just a straightforward transformation of the GEV parameters. So it's not hard to do Bayesian inference here. You just start by, you just draw from the random effects distribution, you apply your transformation. That's how you get one sample. You just keep doing that over and over. All right. So my favorite part, the implementation. So how do you actually do this? Well, the key would be to get to this Laplace marginal approximation. It looks so simple, the mathematical form is so simple, but it's actually, it's deceptively complicated. It's really that you've got to take a log determinant there. That's, that thing could be quite big. That's really however dimensional your random effects are. So it's a huge matrix. So you have to repeatedly do this optimization. So for every hyperparameter value, you've got to get to the mode of that distribution in U. You have to, for various things, whether you're sampling or evaluation or whatever, you need to start computing the log determinant, inverting the Hessian, to even possibly taking the square root of it or whatever. But the thing here is that it turns out, I should have made this more clear, but that Hessian is extremely sparse. Just to shortcut the math on it, it turns out that it's the conditional independence between different things. So as long as, if any of the random effects are conditionally independent, then they are, then there's a zero in the corresponding element of that H. So these matrices typically are very, very sparse, tons of zeros in them. You would want to take advantage of that. You don't want to brute force take that log determinant. And also, if we were really trying to use the best computational methods for inference, we'd actually want to get the gradient of this marginal with respect to the parameter, the hyperparameters, because then we could do, if you want to do mode finding, you get to use a gradient-based approach. If you want to do MCMC, you can use gradient-based things like HMC, nuts, and so on. So this is really useful to use modern algorithms. So what do we have for that? It turns out that somebody actually went out and implemented a nice piece of software to do it. It's called TMB. It's really aimed at our community in the sense that it's like it has a really nice R interface. Underlying code is written in C++. The linear algebra in it is outstanding. It's using the eigen library, if that means anything to you. This is one of like the best, most efficient C++ linear algebra libraries. Does sparsity and so on. Then what they did is they combined this with something called Cholmod, which is like a state-of-the-art sparse Cholesky solver. So they managed to hook this thing in with what was already going on. If you can get the Cholesky of H, you can get the log determinant for free, right? You just add up along the diagonal, or log diagonal. It also gives you a second-order optimization algorithm for mode finding because you've got the Hessian matrix as well. So you can get to the mode in very few steps. You can do random effect sampling, because again, so once you've got the Cholesky, it's like easy to work with, like either multiplying a Cholesky or even solving for a Cholesky. Those are both done really fast. And to just, the cherry on the sundae is that all of this is done with an autodiff. So CPPAD is an autodiff library that has eigen inside it, has Cholesky inside it, and so on. So it's such a simple idea, but the execution of this is key. And I am not aware of any other software that's able to combine all these things effectively. Okay. All right, so I'm just saying what you can do with autodiff here. All right. So just sort of reminding us that what can be accelerated by autodiff here. Okay, so that's point number one. That was how to deal with getting rid of the random effects, so just being able to integrate them out effectively. The next problem, if you recall, was this awful scaling of Gaussian, of working with Gaussian processes, which is essentially the more spatial locations you have, the more the worse the either drawing from the distribution or evaluating the log density is going to get. And you need to do these things repeatedly. Okay, so it turns out that there's a really neat way of doing this. It's a little bit on the theoretical side, so I'm going to try my best to just stay high level where we can kind of get like the essence of what's happening here. So the main thing is it's some sort of basis approximation. Okay, so instead of, we're going to say that this the Gaussian process, where instead of it being an infinite dimensional thing on all of space, it's going to be essentially a combination of a finite number of things. B basis functions, what we got here? Well, so those are the basis functions, and you can just plug in whatever x you want. And then we've got these W's. Those are multivariate normals, so this whole thing at the end is going to be still, it's still going to satisfy that marginal multivariate normal property. And its precision matrix is going to be extremely sparse. So let me try and show you a little bit how this is built up. All right. So here's how the basis is constructed. This is the application I'm going to get to later on, where we have, this is a map of Canada. We had 509 locations in Canada that we're going to use that have some snowfall. And then what we do is we do a triangulation. So for those of you who've done PDEs before, it's the same kind of thing, right? This is like what's underlying the finite elements method. You start by triangulating what's going on here. And so those red dots are all, they're just at various nodes. And then you have these edges connecting them. Okay, so we start by taking the map, and we do this. And as you realize, like in order, there's some, there's like a couple of locations way up here, which are, in order to bridge through all this, it's adding way, way, way more nodes than what you actually need, than how many red dots there are. But it turns out this is so efficient that it doesn't matter that you've tripled the number of random effects you actually have to deal with. Okay, but so what does this look like? I so desperately wanted you to understand what these basis functions look like that I won't even tell you how long I spent on the slide. AI assisted. Okay, so but this is what the basis functions look like. You imagine your triangulation, and every basis function can be associated with one of the nodes. What does it look like? You just take that node, and the basis function is 0 everywhere outside the blue. And it's 1 at the red. So if I take that, all I've done is taken the left-hand side, turned it to the side, and that's what you see on the right. So everything is flat, except in the middle, you just create that pyramid-like shape or whatever, and you have one of those for every single black dot. So the basis functions they mostly don't overlap at all with each other. You can see there's just there's no overlap, but there is some overlap. So they kind of overlap with their neighboring ones. Okay, and indeed, so what we have here is the way this is set up is we're in fact going to build up that this non-overlapping between the basis functions. We're going to encode that into the weights, the multivariate normal weights that are going to be associated with them. We're going to say they're coming from a Gaussian Markov random field. And essentially, the way we're going to set that up is that the weights are going to be conditionally independent of each other given their neighbors. So again, roughly speaking, if you don't overlap, then you're conditionally independent. So the way I look at it here is I say, okay, if I could imagine I've got my red basis function here, every one of those blue dots has a blue basis function, and I'm saying, okay, The red one is conditionally independent of the black ones given the blue ones. So if this is high level, I hope that at least at a high level you're like, okay, I kind of get the general idea here. But if now you imagine this, the resulting precision matrix has got a massive amount of zeros. Because most of these things, there's only so many blue dots around the red dot that have a direct node with it, a direct edge, and that's the only conditional independence. So that precision matrix is extremely sparse. This is great. We know how important sparsity is to Laplace, so it's all tying together. Now, the beauty of all this is how they were able to create this, how they do this triangulation. What is the exact covariance matrix that you end up getting to the W's? I don't understand it myself. I know it's based on stochastic partial differential equations. I also know that the discretization depends on that smoothness parameter nu that I said we weren't going to worry about. So you can't do it for any smoothness parameter all the time. You'd have to re-update the way the base is done. So we just fixed it at 1 nu. That was the way through. But now that we've got all of this, now we have something where we can use Laplace to very quickly get the marginal. And because we have so much sparsity, we're able to leverage that as well. So these are the two key things we put together in order to be able to work with this GV Gaussian process model. OK, a couple of alternatives. So we could just do MCMC sampling from the full posterior. We would get the exact posterior. We wouldn't have to worry about this approximation, which, what people push back, the referee pushed back on us, is when you use Laplace, it's one of those approximations where you can't just throw more computational budget at it and get something better. It just kind of, there's an approximation there. We don't know how good or how bad it is. There's some asymptotics. They're not super satisfactory, so you don't get to retreat into like a theory where you say this is just supposed to work. You just kind of have to demonstrate it numerically and hope that you can extrapolate to something you haven't seen. But if you do MCMC, you don't really have to worry about that. You just get the exact posterior. There's a pretty good way of doing this where that conditional independence was leveraged very effectively. You can parallelize a lot of it. So every step of the MCMC is quite fast. But there's a very high correlation between the random effects and the hyperparameters, and that's going to destroy this. So it's, short story, as you already knew, MCMC is going to be much slower than a mode quadrature finding algorithm. In law, this is like Laplace plus. So this is something that it uses Laplace, but it's much more accurate. Of course, it comes at a cost. In this case, the cost is it's increasing exponentially. You're sort of doing numerical integration on the dimension of the hyperparameter. It starts to really break down. And again, there's also an implementation issue here. We can't just go out and implement an in-law. We need to have a piece of software that does it. It's not easy. The flagship one, the main one that we have, our in-law package, it simply cannot handle this many random effects in this way. It just won't do it. So we couldn't even really do a comparison. It wasn't possible. And the one last thing here that we were able to compare to is max and smooth, which I would like to show this to you. So this is an approximation which is similar to Laplace, but somewhat faster. So I'll try to do this somewhat quickly as well. But here's the idea. You take your model, and then you look at the data level, the top level, and you say, let me just look at that and do a whatever. Maybe you want to do a Taylor expansion, whatever it is, as long as it has this quadratic form. So just take some like mode quadrature. It could be mode quadrature. It could be anything. Doesn't matter. As long as it has this form here. If you've seen this form as many times as I have, you recognize this as like the log of a multivariate normal up to the constant. Well, if that's what this thing looks like, when I combine that with the normal distribution on the random effects, I can do the same inference. If I'm willing to replace that approximation by an equals, then I get to do inference as of this surrogate model. It's not saying anything. This model isn't real. It's just that when you go back to the random effects and the hyperparameters, they would look pretty much the same as for your original model. So your likelihood's about the same. And in this case, since it's the normal setting, you get a nice closed form. This is something really common. Many people have done this. It turns out I was It turns out I'd done this myself in 2016, whereas the paper on Max and Smooth was only published in 2021. And I was just the last of, or not even the last, but in a long list of people who'd done this. But the Max and Smooth folks were the ones who saw the whole overview of how this works. They wrote it up nicely, and they just sort of, put all these just different bits and pieces together into a combined theory. Okay, so let me show you some simulations. So I'm going to show you two of them. One of them is a sort of smaller scale thing here. This has 400 spatial locations, a smooth, and just the true values of the GEV parameters were on these smooth surfaces. Okay, so we're going to do some Bayesian inference with weakly informative priors. Really what that was is that it was just a sort of numerical stability. When we had completely flat priors, things just kind of fell apart. But if you put normal with a huge variance, it just kind of stabilized things a little bit. So this is what the true values look like. And here are the different methods we used. So we had our ground truth, which in this case was exact posterior with the SPD. There's no way around that. That's an absolute must in spatial. You just can't do it otherwise. So HMC nuts, we ran it for a really, really long time on multiple chains, and we decided that's our true posterior. We did, just I'm pulling the figures out of the paper, we called it Laplace MQ. Let's just call that double Laplace. So this is the fastest version of Laplace that you have. So it's just the Bayesian normal approximation, and then you can combine that with a random effects normal approximation too. We could do MCMC on this. So rather than doing mode quadrature, it's still it's the full Laplace approximation. So MCMC on the Laplace approximation, and then for the random effects, it's a draw from that multivariate normal, where we have to recompute the mode quadrature for every draw. And we do the same thing on the max smooth side. Either you can have the double normal approximation, or you do the full distribution of it. So in both cases, there's two levels going on. There's the approximation of the distribution, and then there's the approximation of Bayesian inference layered up on top of that. And then we had a couple of versions of doing that. So here are the results. So let's go through them a little bit here. So the first one is the red curve here, this wider curve, whatever is here in red, that's the true posterior. So what's closest to the true posterior? The only one that's really always there as to true posterior, that's Laplace MCMC. So the only approximation in that case is the marginal, it's not the true marginal, it's the Laplace approximated marginal. But the inference is exact. So it's exact draws from whatever that approximate posterior is. So that one was exact. So the Laplace approximation itself is not penalizing at all in the accuracy here. It's the only one. Oops. Okay. What's the next one we have here? So the next best one in this case is this blue curve here. And that's the corresponding max and smooth. So max and smooth also, it's a little bit worse. Over here you can see this beta got a little bit off. This log sigma got a little bit off here. So it's a little bit worse for shape. Not a tremendous amount worse, still doing much better than the others. Where you're really losing here is when you start to approximate the inference. So in other words, using mode quadrature to approximate the posterior instead of actual Laplace or mode and max smooth posterior. So there you lose quite a bit. And this is something well known about these methods, is that when you start to do these approximations, you do lose something on the marginals. Okay. But now let's turn to the random effects. We got 3 rows here. Top row is ground truth. Second row is fast Laplace, so the one that does the double approximation. Bottom row is slow max and smooth. So I took the fastest Laplace and the fastest, least accurate Laplace, the slower, more accurate max and smooth, and I compared them. In this case, to our eyes, us and the referees, there was literally no difference between the first row and the second row, to the point that one of the referee comments was, "You've made a mistake in your calculations. Go back. There's no way these graphs are identical." Well, to the third decimal place, they're not. Okay, we checked through it. They're not exactly identical, but visually, I can't even see it. Bottom row is pretty good. So this is the best of max and smooth. Most of the time, there's not much difference, little bit. Here's, of course, this is the, what in the paper we went so hard on. There's a difference there. Okay, so and this is, this is on the random effects level. This last column here, this is sort of the one that maybe, we would care about the most in our little application. That's the return levels. So not huge difference, but we are doing somewhat better with ours. So this was, in the paper, this was good enough for us to say, okay, we're going to leave max and smooth behind. Let's just focus on our method. So I'll just, I think just in the interest of time, I won't get into this too much. All I want to maybe read just quickly, so bottom row there is just the ratio of standard deviations. So far I've only been comparing things in posterior means. The bottom row there is the ratio of posterior standard deviations between true and our fastest approximation. And I just wanted you to see all these numbers, like the whole range here is between 0.95 and 1.02. So standard deviations are matching very closely as well. So it's accurate in this simple simulation. I'm just repeating myself. Maybe again, let's just move on. Again, it's the same story here. We're very accurate compared to other methods. This last line here, KS, this was a bit of a distributional comparison. So we did there, as we said, at every location, you have a posterior of the return level given the location. We take those two posteriors, we essentially compute like a Kolmogorov-Smirnov statistic between them, and we do that at every location. So we had, in this case, 400 locations. We had 400 Kolmogorov-Smirnov statistics, and then we just average them together. So that's why there's a 0 in the first one, because you're comparing the same distribution to itself. And then we got a nice low number here for what we were doing with Laplace, quite a bit lower than max and smooth. And finally, the last bit here, this is just the runtime. So 18 seconds, 14 seconds for our fast methods. I timed out on computing how long this was, but it's several in hours, like a relevant unit is just, it's a lot. And it's clearly many orders of magnitude faster than the fastest one. MCMC would be great. As I told you, MCMC with Laplace is fast. You're gaining a lot, but like you also have sacrificed quite a bit, right? So it's like now it's not an order of magnitude difference. It's a 4 or 5 times difference. Is it worth it then? I don't know. It's up to the experimenter to decide. But that's what we had for simulation 1. Simulation 2 was more complicated for 2 reasons. First of all, it's 6,400 locations. So that's 80 by 80. This is a lot. This is, and I'll show you what the computing time or memory is on this. Again, same weekly prior. This is just what it looks like. So it's not smooth. We generated this with some Gaussian process, not the one that we're using for inference, but we're using something a little bit different here. But this is what it looked like. So these were ground truths that we generated once. The competing methods in here, we just did Laplace just the fast Laplace. This took 22 hours just to find the mode here, and 90 gigs of memory. As a basis of comparison, for HMC nuts, 100 steps took a week. It wasn't nowhere near convergence, so we just abandoned it. We just left it at timing. So we don't have a ground truth to compare to, but when we just kind of looked at inference, it seemed okay. The estimates weren't too far from the truth. That's the top row. So this is posterior mean versus true value. The bottom row was we tried to do these z-scores. So we're sort of trying to get to a distributional thing. So we figured if we had the exact true posteriors, then the actual value would be, where would it lie? We would expect it to be coming from the distribution. It should look like a random draw from the distribution. So if I have my actual posterior distribution, then the truth should look like random draws. So we rescaled that into these z-scores. We take true minus posterior mean divided by posterior standard deviation, and then we just did like a QQ plot for that. So how far those fell on the normal. And I mean, it looks reasonably good, right? We've seen worse. It's of course not perfect, but it's, this is how we sold it at the time. So we're doing, okay in simulation. All right, so we can get to the case study now. So it started off with, we had about 4,000 weather stations recording monthly snowfall in Canada over a 30-ish year period. And then out of those, we said, okay, let's look at the maximum snowfall in a given year in a given location. So you pulled out these maxima. We decided we wanted to have at least 10 years of data per station. So that left us with only about 500 stations to look at. And as this is the same figure I showed you, so this was the gridded version that we used to do this. So in this case, like I'm repeating myself, but like the random effects that we dragged around in the Laplace approximation is all the nodes in this graph, not just the 500. So there's way, way more. But again, it's this data augmentation principle that even though there's so many more locations here, because the corresponding precision is so sparse compared to a dense one for the fewer, it's zillions of times faster. Okay, so here's the models we looked at. They're all GVGPs, but we just looked at a few variants of it. So one of them was only the location is random, is location dependent. Everything else is fixed. The other one was location and scale are random, and only the shape is fixed. And finally, we did they're all random, so the fullest model. Well, we found for that one, when we did this, is that the shape estimate was basically, they were just hovering around 0 on the original scale. So it all just kind of looked like gumbo. We were like, all right, let's just save ourselves the trouble and just move to the gumbo. So we just treat S as fixed in this case. We didn't need the full GVGP for this analysis. So here's the checks that we did. We tried to do, like, it's a posterior predictive check. I can write down what it is, but like you would think of it as like we have a test statistic. It's essentially a sort of goodness of fit. We're going to do a type of goodness of fit, a Bayesian goodness of fit for each of the models we're going to keep here. So let me see if I can walk you through how it would work. So you start by saying, for every location, I'm going to give myself a test statistic. That this just depends on the data at those locations. So in this case, it would be, we're going to say, okay, the median of the 10 plus locations or the top 10% of the 10 plus locations. So those are the two test statistics we looked at. Well, it turns out that we can compute a predictive posterior for this. So how does this work? The mental model is this. You have a posterior distribution for the hyperparameters. Now just regenerate data at your same locations in this case, but by simulating where you do a draw from the posterior and then a draw from the data model. So this is like the replication distribution. This is called the predictive posterior. It's a bit like, it's weird to think of prediction because you're predicting at the same locations you've already seen. It's not an out-of-sample test in this case. It's an in-sample thing. But I would think of it as like, if the posterior predictive distribution looks nothing like your actual test statistic there, that's bad. So this is, it's a standard, it's a standard goodness of fit Bayesian test, and that's what we did here. So after that, it's your good old sort of p-value thing. You just look at where the observed value falls in the distribution of your predictive posterior. Okay, so top row in this case, this is the location scalar random. This is bottom row is only location is random. Left is medians, right is upper 10%. We tried to set this up in a way where we were looking at, these are like, again, we did this like QQ plot kind of thing. So we look at, you can think of that at every location now, you get a p-value, a posterior predictive p-value. Just take the inverse CDF of a standard normal to convert it to a z-value, and then just do your good old QQ plot with that. So again, we would, if the model were perfect, then these dots would all fall along the 45-degree line. They clearly don't. There are some departures, but there are more departures in the location random only compared to both the location and scale being random. So we went with location and scale being random. This is just a bit of the inference that we have here. So now we're looking at the return levels. This is what we were able to get from this. We only did it at the observed locations. I wish we'd just done the whole heat map because we could have, but we didn't. So on the left-hand side, we have the posterior mean. The right-hand side, we have the posterior standard deviation. Some of the dots that we looked at here, there was this one here down in, this is just in Waterloo, because that's where we were. And we can see, okay, there's not crazy snowfall happening, and we're pretty sure of that. So the standard deviation is small, small. Whereas we had some locations here with very high snowfall, and we look at the standard deviations. Well, in one case, we're pretty sure of that because it's small. But in this case here, it was just a sort of data sparsity issue. There just weren't that many locations around here to borrow information from, so the standard deviation is wider. So it sort of makes sense. I'm at the conclusion here, so just to maybe briefly summarize what we have here. So the GV-GP model itself, so the hierarchical model we use, GV at the data layer, Gaussian process at the random effects layer. Speed and scalability, we achieve this with a combination of Laplace and this sparsity-inducing SPD approximation. Spatial GV, this is our software. It's available. It's on CRAN. It's also it's built on TMB. I encourage you to use TMB for this if you like. It's all like SPD is built in there as well. You don't have to build your own. Where we want to go with this is one of them is I would love to the way this is set up is you're kind of boxed in with R to use this. It's I've looked at the underlying TMB code a million times. It'd be very difficult for me to translate this or to even just port that C++ to something else. Maybe now with AI, this is a lot easier, but at the time, this was like really difficult. So I'm interested in trying to connect this to other things. Again, if you want to like connect this with anything neural network, you can't do it from R. It's just, it's not going to work. I'd love to improve the accuracy of Laplace. There is a way of doing this, which is this. Just imagine instead of, there was a conditional normal we were using and we were putting that in the denominator, but instead you could take that conditional normal and just use that as an important sampler. So do draws of that, and now in some sense, like you're unbiased in some way. You remove that thing, and you get to have a knob where the more draws you take, the more accurate you are. So this is good, but there's also a price. Once you allow yourself for the approximation to be perfect, it takes a lot more computational budget before it looks good. So there's got to be something in the middle, where the theory is still there. Like it still performs well when you're doing it, but you don't, you get the theory, you get the best of both worlds. We want to do more spatial temporal modeling. I should have inverted these, but the neuroimaging project, that's something that that Reza and I are continuing to work on. And then air quality, that's something new that I've launched into recently, and that I would like to apply some of these techniques to that. And that's the end of the talk.
Any questions from the audience? How will you go first?
Hi, thank you for the great talk, really interesting. Maybe a bit of a naive question. When you showed your map of Canada for your application, I noticed you had like a disjoint region all the way up north. Does that cause any added complexity to inference, and or is it just accommodated directly with your model?
That's a great question. As I'm cycling back, I'll start answering. So I'll just repeat it, like in case, just in case anybody didn't hear. So it was about the data here. So with the sharp observation was that you'll notice there's one dot up here, and there's like one here and one there. There's a few dots over here. This was something where it would probably, okay, it's likely that this analysis, if we just restricted ourselves to everything below the 60th parallel, it would have been like, more homogeneous in a sense. It would have been, we'd say, okay, we ignore what's above 60th parallel, but whatever we're doing below, it's now better on that. It would have been faster because we have less points. It would have been maybe more consistent because we're grouping things together that are kind of closer. We didn't notice that until we were like 2 revisions deep, just wanting to get this paper done, and so we just left it there.
Yeah, just a couple of questions. I'm curious, so you had registration data, so why just snowfall? Maybe why not precipitation or other variables? And then I'll ask the other one later.
No, that's a great question. So why do we focus on snowfall here? I think this is an illustration passed off as an application. That's the real reason. So we just need to have something to make this a bit more palatable.
The other one guys consider like out of sample prediction or some sort of test
We,
set?
we did.
That would have been
It would have been.
solid test.
I completely agree. This is like, again, there were so many things we wanted to redo, and this is where, like, I'm so grateful for Meixi, was like, we just need this paper done. Like, we just need to do this. And like, the other thing is, I was terrified that if we really do out of sample, it's going to look much worse. So the referee didn't push us on it. We just let it go. Yeah.
Good point.
Illa use Laplace and then what the difference between MCMC and Laplace MCMC and Illa?
Okay, so in-law is, okay, so there's two levels going on here. The question is, what's the difference between Laplace MCMC and in-law?
Yeah, the two approaches use two procedures, right? First they use Laplace approximation and then MCMC.
Okay, so yes, so here were the different steps. There were two levels of approximation going on. One of them is approximating the true posterior by an approximate posterior, either Laplace or the other one we compare to is this max smooth. So those are two posterior approximations. They both give you something which is a posterior. The next thing was, how will you do inference on that posterior? So in those cases, you could just do MCMC, which is like exact inference for approximate posterior, or we did approximate inference for approximate posterior. So that was just the mode quadrature. Yeah. In-law is a better approximation of the posterior than ours. Our in-law is a piece of software which I don't know whether it does MCMC or something else. My guess is it's not MCMC because it's so much slower. So they must use some other approximate inference on their approximate posterior as well. That's my guess. Yeah.
Thank you. Any other questions? Please. No, then ask Zach, no, speak Martin again.